Fundamentals, physical quantities, units, and vectors. Let's explore essential physics concepts including measurements, vector operations, and unit analysis for fundamental understanding or foundational. So let's master these physical quantities and units. First, we're going to define the physical quantities and units clearly. We need to be able to understand physical quantities such as length or mass and how units such as meters and kilograms provide standard measures for expressing these quantities. Next, identify base and derived SI units. So we need to learn the difference between base units like meter, kilogram, seconds, and derived unit formed from these. Essential for consistent scientific communication. Next, recognize the importance of significant figures to grasp how significant figures convey measurement precision, ensure accurate and reliable data recording and calculations. Next, differentiate scalars and vectors to explore scalars and magnitude only, and vector magnitude and direction, including examples like speed versus velocity. And lastly, we need to learn how to analyze vector components and perform vector operations. So we're going to break into vector components and use unit vectors for direction and apply scalar and vector products to solve physics problems effectively. So let's explore vectors and scalars and the key differences. So let's start with the definition. So the property scalar is quantity with magnitude only. So anything that describes quantity with only a magnitude is considered scalar. Meanwhile, vector is quantity with both magnitude and direction. So examples of this. So temperature for scalar, it only provides a magnitude. There is no you cannot define the direction in which temperature of a place is. You can describe the temperature of a specific place, but the force in which, for example, a wind blows is a vector because it describes a magnitude and the direction in which the force is going. Other scalar examples are mass and time. Other vector examples are displacement and velocity. So scalar property is represented in numerical value and unit. Meanwhile, vector is represented with an arrow and length, which shows the magnitude and the direction in which the example is going, such as force. Now for scalar property, mathematical rules is we use addition by arithmetic addition. Meanwhile, vector, we add using vector addition rules, so triangle and parallelogram laws, and we'll get into that right next. So first, let's go into mastering the vector addition and using graphical and analytical methods. So the triangle rule for vector addition. So in this case, we have a ship that this man is standing on, which shows a direction in which the ship is going, and there's a magnitude of that force that is causing the ship to go down into the ground, which we'll get into soon. But if you were to draw, so we'd place the tail of the second vector at the head first, and the resultant vector will run from the tail first to the head of the second, illustrating a sequential addition. So a parallelogram has 4 sides. So here you'd place both vectors tail to tail to form a parallelogram, and the diagonal represents the resultant vector. The difference between a parallelogram and a rectangle is that there is a diagonal that is slanted versus a rectangle which is completely straight, vertical and horizontal lines. So if you have that imagery in your mind, then you can understand that the lines are forming a parallelogram. Only difference with a parallelogram and a rectangle vector is that there is arrows. So the analytical vector addition breaks vectors into x and y components and adds algebraically. Resultant components equal sum of corresponding components. Example of vector addition is this first algebraic equation. So a is equal to 3i plus 4j, or let's do the next one, b is equal to 1i plus 2j. So these two yield the resultant 4i plus 6j. So if you add 3i plus 4i, you get 4i. 3i, sorry, plus 1i, you get 4i. 4j plus 2j, you get 6j. So next, we're going to learn step to step how to break vectors into components, which simplify problem solving. So let's speak about vector decomposition. So any vector can be broken into perpendicular components on an x and y axis, enabling easier analysis and equation. So again, let's imagine a parallelogram, four-sided geometrical object or geometrical shape, which has slanted or diagonal sides on one side and then the other is straight. We can use trig. If we were to split a parallelogram into half, it will create two triangles, and you can use trigonometry to calculate components by applying cosine sine functions based on the vector's angle relative to the x-axis. Why use components? So we use components to simplify vector addition physics and physics applications by converting vectors into manageable scalar parts. Scalar, what do we say, is magnitude only. So practical example. So let's say we have a force which is 50 newtons, that's the SI unit for force, at 30 degrees split into 43.9 newtons horizontally and 25 newtons vertically. So again, imagine we have two triangles. We have one side of each triangle would create a angle at the point at which the triangle splits the parallelogram. So there's three angles, well, three main angles in said triangle. So if we imagine that, then we'd have six angles in the parallelogram. So for the first triangle, we're gonna have 30 degree splits. So this could be an equilateral triangle in which all the degrees, never mind. It's not an equilateral triangle, and I'm not gonna give that to you guys as yet. But let's just say we have 30 degrees. That is where the split is of the parallelogram. We have 30 degrees at one top end, and then we have a 50-degree force. So we'd use the top side that is straight to signify that is 50 degrees, and then the other side to say 43.3. And the last force would be the force or the resultant force, which is the same as the same line that would split the parallelogram. So it'd be the same for both triangles. So then if you have those two values, then you could use it to find the value of that side using trigonometry, using cosine or sine, SOHCAHTOA. So in this case, we have one angle and we have a side x that we're trying to find. So we have 30 degrees. So we're trying to find opposite. We're trying to find the hypotenuse. So we could use sine. We could use sine actually, because we have opposite. And we could do sine 30 degrees equal to x over which one we want to use, 43.3 or 50. And that's how you would solve that problem. So let's master unit vectors with directional representation. So we have a lot of mathematics that's happening here, and it's just the use of science so that we could break it down. But just know that in any case, a unit vector has a magnitude of exactly 1, which represents direction only without magnitude, right? So when you're expressing a vector using unit vectors, it can be broken down into components along the coordinate axes. So we spoke about x, y. It can also involve z. And when we break it down in these ways, then it can make the calculations pretty straightforward. Calculating unit vector by dividing the magnitude. So a unit vector of any vector can be found by dividing its magnitude, right? So we can use vectors provided a standardized way to denote direction without considering magnitude, helping simplify physics problems and vector operations. So an example is this last one, and I'm actually gonna skip just so I can show another example later on. But first, let's master scalar and vector products with key formulas. So, explore how dot and cross products work and their practical physics applications. So, a scalar product, which you said, remember, magnitude only, yields a scalar value from two vectors, and it's calculated using magnitudes and the cosine angle between them. So it's also sums component-wise products and measures projection, such as work done and force over displacement. Defining vector cross products. So a vector product produces a vector perpendicular to both input vectors, determined by magnitude, sine of the angle, and direction via the right-hand rule. This is calculated with a determinant for component form. So example of vectors. So here are two vectors. We have A, which is 2i plus 3j plus k, and b, which is I minus j plus 4k. So to compute the scalar product, you do the sum of the component multiplication. So similar to the example before, we have algebraic equation where if you were to calculate the sum of both, you'd have 3i plus 2j plus 5k. So let's speak about real world physics and how vectors and scalar apply. So when we're analyzing forces in equilibrium using vector addition, you determine the net force by adding vectors to confirm the total equals 0, ensuring the system is in a stable equilibrium. This is extremely important for safety and balance. Next, when we're decomposing velocity in projectile motion, to break down the velocity vector into horizontal and vertical components to predict trajectory and time flight accurately, essential for ballistic and sports physics. So calculate work using scalar product. So when we use the dot product, so to find work done by a force along a displacement, we link direction with energy transfer. And then lastly, determine torque and angular momentum via vector product. So apply cross product to compute torque, vital for analyzing rotational effects in mechanical system like cranes. So those are real world applications. So thank you for watching the introduction to physics, university, or it can be high school as well. But this that we just went over was units, physical quantities, and vectors. If you're interested in learning more about the chapters that we're going to continue into, the next will be motion along a straight line. Just to go over what we went through, we went on the nature of physics, solving physics problems, standard and units, significant figures, vector addition, components of vectors, unit vectors, and product of vectors. If you'd like to get more examples and to go through practice questions, please like and subscribe, and I'll definitely get that to you.